So we're going to take everything that we've been doing in this unit and tie it all. Really, the whole goal is to be able to solve real world problems. So these are trig problems. We want to remember our SOHCAHTOA. Remember that sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. So we're going to set up problems exactly like we've been doing, but we're going to create our pictures from the words that we have in the problem. Now there's a couple of vocabulary words that we need to know, and that is angle of elevation and angle of depression. Now what you really need to know is that there isn't much difference between an angle of elevation and an angle of depression in how it works. In what it means it is, but we have to know that we could use this same triangle upside down or right side up, and this triangle are the same. Now what happens is, if you look at this, the angle of depression is the angle looking down. So you have somebody up and they're looking down, so it's from the horizontal down. Okay, notice that both angles are based off of the horizontal, not the vertical. So horizontal, that is a line that goes like this, right? Your x-axis. Okay, then you've got your angle of elevation. Your angle of elevation is from the horizontal up. Now notice that these are alternate interior angles. And what we know is that horizontal lines are parallel. So if this horizontal line is parallel to this horizontal line, that means that these alternate interior angles are congruent. Okay, so in the end, it doesn't matter. Now, here's what I need you to be careful of is this is not an angle of depression. That's where everybody wants to put it, but this is a vertical line, and that would be the angle off of the vertical. Now, there are some situations where that could happen, but it would be specified. If I ever call it an angle of depression or an angle of elevation, then what you want to do is draw your triangle, find your horizontal line, and that is where your angle goes. Whether you draw your triangle like this or whether you draw your triangle like this, right? This is your horizontal line, so your angle of elevation or your angle of depression would go right there. They always go in the same place, okay? And it's off the horizontal. That's the important part. So let's look at some word problems. Let's see how we set them up and how it is going to look exactly like what we have already been doing. Let me make sure I have a calculator that works. Sorry about that. Okay. So a ladder leaning against the wall. So imagine in your head that you have a ladder. You're standing over to the side and you can see this ladder leaning against the wall. It makes an angle of 74 degrees with the ground. So here's the ground, and the ladder between the ground, the angle between the ground and the ladder, which is this angle right here, is 74 degrees. If the foot of the ladder, here's the foot of the ladder, is 6.5 feet from the wall. Here's the wall. So it is 6.5 feet from the wall, from here to here. How high on the wall is the ladder? So I want to know how high up I can reach. So that is where your variable goes. So now forget the words. Just look at your sides. So go back to our steps, just like we've been doing. Determine what sides that you have. Label your sides. So x is opposite of the 74. So this is our O. The 6.5 is adjacent to the 74 degrees. And so I want to use O and A. O and A is tangent. T-O-A. O-A. So tangent. So to set up the formula, it's the tangent of the angle, which was 74, is equal to the opposite side, which is x, over the adjacent side, which is 6.5. Okay, now this is a multiplication problem because we need to do the inverse. This is x divided by 6.5. If you need to, you can always put this over 1 and cross multiply. So you would do 6.5 times the tangent. So x is equal to 6.5 times the tangent of 74. Make sure your calculator is in degrees, so you would type it in just like that. 6.5 times the tangent of 74. And that's what I was talking about, making sure. I need to make sure So 6.4 times the tangent is 74, and you get 22.67. So x is equal to 22.7 feet. So it will reach 22.7 feet up the wall. Okay? So again, we've given you some real life pictures so you can kind of see what it looks like, but we want you to be able to see that. So you've been hired by the National Park Service to measure the height of Old Faithful. Okay, so we want to know the height of Old Faithful. You stand 20 feet from the base of the geyser. So there's 20 feet. Here's you over here. You are 20 feet from the base of the geyser. You record an angle of elevation of 80 degrees. Okay, so remember, angle of elevation. Angle of elevation from the horizontal up. So 80 degrees goes right here. Off front. Here's your horizontal line, and it's going to go up. Okay? So you're 80 degrees there. How high to the nearest foot is the geyser? So here's what we want to know. We want to know how tall it is. Okay? So that's our picture. Again, we do the same thing that we've been doing all along. We label our sides. So from the 80 degrees, the x is opposite. The 20 is adjacent. So that means I want to use tangent. Set it up. The tangent of the angle, which is 80, is equal to the opposite side, which was x, divided by the adjacent side, which is 20. If you need to, set it up like a proportion so that you can see it, or just recognize that you're going to do times 20 on both sides, times 20. So x is equal to 20 times the tangent of 80. So you would type that in. 20 times the tangent of 80. Notice I didn't type in the multiplication this time. That's okay. You don't have to. You can, but you don't have to. Which means that the geyser is 113 feet tall. The 0.4 doesn't round it up, so it says it wanted it to the nearest foot. To the nearest foot means to the nearest whole number, so you would leave it at 113 feet. So it's about 113 feet tall. That's how high it sprays. Okay? So you can't see this picture very well, but there's a lighthouse, and then there's a ship out here. A man on top of a 191-foot lighthouse, so we have a 191-foot lighthouse, spots a ship in the distance. Okay, and he's up here. So he's up here and he's looking down at this ship. If he measures the angle of depression, remember that's from the horizontal down, at 27 degrees, how far is the ship from the foot of the lighthouse? Here's the foot of the lighthouse, and here's the ship. So the question is asking, how far is that? Now the problem is, where does the angle go? If you remember, the angle of depression and the angle of elevation are always based off of the horizontal line. Well, this is the horizontal line. This is a 90-degree angle. This is the horizontal line, which means then that this is 27 degrees. Now, technically, right, I know angle of depression is from up looking down. Okay, so technically what it is you invert that triangle and you look at it upside down like this. Then that would be 27 degrees, but you would have to know to put the 191 over there. So that's why I always just like to draw the triangle, find the horizontal, and put my angle of depression or my angle of elevation where it's supposed to go. So now we label our sides just like we always do. From the 27-degree angle, the 191 is the opposite side. The x is the adjacent side, and again, that's tangent. You can see how effective tangent is. It's very useful. So the tangent of the angle is equal to the opposite side, 191, divided by the adjacent side. Don't worry about the math until you get it set up. Now, again, this is where it might be useful for you, since we've been doing similar triangles, to set it up as a proportion. So you can see that when you do the math, you get x times the tangent of 27, remember that's a number all on its own, is equal to 191. And then you would divide both sides by the tangent of 27. So you would type in 191 divided by the tangent of 27, and you get 374. So the ship is 374.9 feet. And a test and a quiz, we will, sorry about that, we will let you know what you need to round to, okay? So about 375 feet is how far the ship is from the bottom of the tower, okay? So we've got this ski lift going on right here. The chairs of a lift at a ski slope are attached to a cable that is 4,640 feet long. The vertical change of the lift is 2,178 feet. What is the angle of elevation of the lift? So here we draw it in, but basically here is my cable. It is 4,640 feet long. And then your vertical change, so how much did you change up and down from when you were down here to when you were up here? It was 2,178. The question is, what is the angle of elevation? So find your horizontal. Here's your horizontal. And that's where we're going to put our theta or our x. You can put whatever variable you want to there. Now we've got our triangle, so let's look and see how we label it. So 2178, that's opposite of the angle, and 4640 is on the hypotenuse. That's O and H. O and H is sine. Sine so, right? S-O-H. So we say the sine of the angle is equal to 2178 divided by, opposite divided by hypotenuse. Now, as much work as you need to do, whatever you want to do, right, what we want to do is inverse it. We need to separate that sine theta. So what we want to do is we want to inverse it. So we're going to inverse this side. We're going to inverse this side. So theta equals the inverse sine of 2178 divided by 4640. So you type it in on your calculator. Now remember your inverses. They're right here. In blue, right above the sine, cosine, and tangent is your sine to the -1, cosine to the -1, and tangent to -1, or your inverse. So you hit second sine so that you can get your inverse sine, and then 2178 divided by 4640. And you find out that the angle is 28 degrees. So that is a 28-degree incline. Okay, that's your angle of elevation of the lift. So this is like a real world problem that you might have to do if you work for a city. You might have to calculate these things. The Uniform Federal Accessibility Standards specify that the ramp angle used for a wheelchair ramp must be less than or equal to 4.78 degrees. So what that's saying is, if we kind of assume this is a straight ramp like that, that this angle right here has to be less than or equal to 4.78 degrees. The length of one ramp is 16 feet. Now think about where the ramp is. This is actually the ramp, right, on the diagonal. So the length of the ramp is 16 feet. The vertical rise, or the up and down, is 1.5 feet. Find the angle of the ramp to the nearest hundredth. So what we're looking for is that angle right there. We want to know, does this meet the UFA standards? If not, what would you do to fix the problem? So we're looking for the angle. We need to label our sides. So the 16 is the hypotenuse and the 1.5 is opposite. So we're going to use sine again. The sine of the angle, every time you set it up the same way, the sine of the angle is equal to 1.5 divided by 16. So theta is equal to the inverse sine of 1.5 divided by 16. So we're going to type that in, inverse sine of 1.5 divided by 16. And we get 5.4 degrees. So theta is 5.4 degrees. Okay, so the maximum is 4.78 degrees. So this is a lot more than that, that maximum that it can be. So it can't be any more. So what could you do? Well, you could lower the ramp. You could make the ramp longer, which would pull it back like this, make it cover more space. I mean, the 1.5 really can't change, but what you could do is you could create 2 different ramps like this and still have it cover the 1.5, but have it do it a little bit at a time. So there are a lot of options for how you could fix that, but it definitely needs to be fixed because it's too steep. The last one, you're flying a kite with 20 feet of string extended. So here's your kite, and you have 20 feet of string extended. That's where your string is. The angle of elevation from the spool of the string to the kite is 41 degrees. So we always have our horizontal. Every picture is always going to be a right triangle of some sort. The angle of elevation from the horizontal up is 41 degrees. How high is the kite if you're holding the spool 2.5 feet above the ground? So you're holding the kite 2.5 feet. Now you notice that 2.5 feet is outside of the triangle. So we're going to come back and deal with that in just a second because we had to put our horizontal right here and it's up off the ground. So let's find H. So H, that's opposite and that's hypotenuse. So again, we're going to use sine. So the sine of the angle, which was 41, is equal to the height of the kite, the vertical opposite, over the hypotenuse, which is 20. So in order to solve this one, we need to multiply both sides by 20, and you type it in. So H is equal to 20 times the sine of 41. You get 13.1 feet. So the height above where the spool is 13.1 feet. That's this piece right here, 13.1. But I'm holding it 2.5 feet above the ground, so I need to add the 2.5 feet back in. So the kite is actually 15.6 feet off of the ground because we didn't connect the kite to the ground. If it doesn't tell you how high off the ground that you're holding it, then the assumption, you have to assume that you're going to negate this, that you're not going to pay attention to it, and that it's minimal in the realm of things. And so if you get that, if you're given that information, then you would add it back in. But if you're not, you would just do it as though the kite's been tied to the ground. So everything is just like what we've been doing as far as solving the equations, but every one of these pictures has turned into a right triangle with an angle of elevation or an angle of depression, always off of the horizontal. So find your horizontal line, and that's where your angle is going to go. Set up your problem with your pictures, label them, set up your equation, and solve your equation.